Hello folks, how are you guys doing? Recently we had been getting quite a lot of inquiries from our viewers requesting for an explanation on DC to DC converters or rather like voltage regulators. So we thought of making this video which will actually explain how the internals of these circuits work. Today in this video we'll be going through linear regulators, their operation and understanding, different types of linear regulators like variable, fixed, LDOs, why linear regulators are not that efficient. So we will try to figure out some power dissipation equations and how they operate. And then finally we'll see the switching regulators. We'll try to understand the operation details of the switching regulators. And then we'll close the video by conclusion and comparison between these two regulators, which is like linear and switching. So today our problem statement stands to understand and analyze the functionality of this building block regulator, which is capable of taking a DC voltage input and can deliver a DC voltage output, obviously to drive some sort of a electrical load. These type of power supplies or regulators are very much common and is a basic building block of any PCB or any electronic circuit. But before we start, let us first try to understand the basic characteristics or the basic requirement of a voltage regulator. Number one is Vout, which is output voltage, should be agnostic of any changes in the Vin. That means with variations of input voltage Vin, the output voltage should be steady and should be constant. And secondly, Vout should be stable with varying load. So in case the load varies, which draws more current, Vout should not be altered or should be stable in such conditions. So Vout is basically should be independent of Vin, as well as Vout should be stable with changes in the load resistance. So we will concentrate in this discussion on scenarios where Vout is less than Vin, and these are basically known as buck converters. So when we talk of a voltage step down of a DC voltage, the first thing that comes to our mind is a voltage divider circuit. It's a simple circuit with two resistances R1 and R2 connected in series across an input supply Vin, and the voltage out is tapped across resistance R2. With simple Ohm's law, you'll understand the current that flows through this loop I is basically Vn divided by R1 plus R2, right? And the same current flows through R2 as well. And the drop across R2 is Vout. So with the same Ohm's law, Vout by R2 is the same current which flows through this whole loop. And these two are the same parameters. Now equating this, we can now calculate the value of Vout. So Vout here is basically, with this equation, is R2 divided by R1 plus R2 multiplied Vin times. So if you see, we have actually made a voltage Vout which is in proportional to Vin, and we are able to reduce the output voltage by this factor. But are we able to achieve the purpose of a regulator? No. The reason being, the output voltage Vout is now a factor of Vin. So whenever Vin varies, if it increases, Vout will also tend to increase. And if Vin decreases, Vout also will decrease. So this defies the purpose of a regulator. So the output voltage is not stable. It is dependent on Vin. Moreover, the output voltage is also altered by the load resistance. So if we have a load resistance here, which is RL, and if RL varies, then this equation will vary, which will in turn alter V out. So V out is now dependent on V in as well as RL. So even though we are able to convert V out and from V in, we are still not able to solve the purpose of this regulator. So what is the solution for this? The solution is to deploy some sort of a logic circuit which has a reference voltage which is constant, and V out, somehow if you are able to manage to make it as a factor of Vref, we call it V reference. So if V reference is constant and V out, if somehow we are able to make it dependent on Vref only, then we will be able to stabilize V out, because Vref is stable from voltage point of view. However, with changes in the load resistance, if the current demand varies, if this current demands I load varies, then this logic circuit should have some sort of a provision to draw the current and directly from V in. So we need to design some sort of logic circuit which will solve to draw current from V in directly, as well as to have a steady state voltage with respect to Vref. Now, this is the internal circuit of a regulator. Let me try explaining the components of this. Number one, we have a switch. It is an electrical switch which can be made on and off depending on the gate voltage. So if the gate voltage is 0, the switch is on and the current flows from the source to the drain side. And if the gate voltage is high, this switch is off and no current flows through. The block here is an error amplifier, which is basically an operational amplifier. It has two inputs. One is an inverting input, one is a non-inverting input. Here if you see, we have the steady voltage Vref, which is the internal reference voltage, feeding the inverting input of the op-amp. So before explaining details of this circuit, let me quickly try to tell you how this error amplifier actually functions. So this error amplifier, try understanding this as an amplifier of the error. So assuming that A and B are two inputs, and if A is greater than B, so the difference is A minus B. So it will amplify this and make the output positive to the maximum voltage to which this op-amp is working at. And if A is less than B, in that case the output will be the minimum voltage at which this circuit is working at. So the job of this op-amp is to drive a logic high or logic low depending on the difference between these two voltages. And this op-amp or this error amplifier will try to maintain voltages between these 2 points always at the same level, at the same potential. So in the process of maintaining the same potential at these 2 points, if one of the input is varying, the output will vary so that the voltage between these 2 points remains the same. So V feedback will always be equal to Vref. And in the process of doing so, the error amplifier output will be either increasing or decreasing. Now let me try explaining you how this circuit actually works. The output is tapped out of this point V out. So the current that is running through this loop is basically V out divided by R1 by R2, again by Ohm's law. At the same time, the same current is flowing from this point to the ground terminal, and the potential drop across this resistance is V feedback. So same current, since it is flowing through, is V feedback by R2. At the same time, this op-amp is making sure that V feedback is actually equal to Vref. The property of this logic circuit is that it tries to maintain the two input voltages at the same level. So our second equation is V feedback is actually V reference, which is basically constant voltage. And solving for these two equations, you will see that V out is now Vref 1 plus R1 by R2. So in fact, what we have tried achieving by doing all this thing is we have we are able to generate V out, which is now proportional to V ref, which is a constant voltage, which was the idea. So now V out is no longer dependent on V input. At the same time, V out is also not dependent on the load resistance. So let me try to show you how it happens. Assuming we have one load resistance here, which is RL. So if there's an increase in the current through RL, the voltage V out might drop. So if V out drops, the V feedback will tend to drop because it is tapped out of V out. And if V feedback drops, the V gate output will be negative, which in turn will make this switch on for longer duration of time, and V in will conduct even further and increasing the voltage V out. Let me try to explain you this a little bit further. Here is the error amplifier with the two inputs V feedback and V reference, and output is V gate. This is the same circuit which I have tried to draw it here. So the logic works this way. If the load reduces, the current actually will reduce. This current will reduce will actually increase V out. If V out is increasing, which actually means the V feedback, which is the tap out point, will also increase. Now if V feedback is more than V reference, then the V gate will be positive. If the V gate is positive, that will actually turn off the MOS because it's an inverted MOS, and therefore this current will not flow through. On the contrary, if because of increase in the load, or if more current comes through here, which is IL, if increases, which will cause a drop in V out, so V out will drop. If V out drops, the feedback will be less than the Vref. So this feedback path will be less than Vref. So this will make Vg to drop, or Vg will be negative. If Vg is negative, this switch will now become on, and this will allow more current to flow from the source to the drain, thereby increasing V naught. And this is how the regulation actually happens. So if the output voltage is dropping, this error feedback loop will try to bring up the voltage so that it again becomes constant or stable. And when V out increases, this feedback loop will again try to pull it down to bring to a stable voltage of V out. However, some people might argue, why don't we use an NMOS here instead of a PMOS? Is it possible or not, so that we don't have to do a negation on this? Yes, it is quite possible. So all we need to do here is make an NMOS and invert these two. Okay, so now this is how the whole system is going to work from here on. Actually, in the earlier case, it is quite possible to make the PMOS fully on, where V out will now be equal to V input. But since Vg cannot be less than 0 volts, therefore the V in has to be something more than the threshold voltage of the gate, and that is around like 2.5 volts for the PMOS for these sort of transistors. And therefore those linear regulator does have a voltage in which V in has to be actually more than 2.5 volts to operate. Using an NMOS transistor here actually helps in reducing the dropouts. This is known as the dropout voltage. So it helps in reducing this dropout voltage by simply using an NMOS transistor here, and these NMOS transistors can now work at as low voltage as say 1.5 volts and so on, and can still deliver outputs up to say 1 volts or like 1.2 volts at even higher currents of 1 amperes. And this is basically an LDO, which is a low dropout regulator, which incorporates NMOS transistors here and then negation of the signals, which was earlier in the case of a normal linear transistor. So quickly, this is the circuit diagram of an LDO, which I was just discussing. It has an NMOS transistor here. Sometimes to make it on, we might require some internal charge pump or some sort of external bias voltage to turn on and off on this switch. So far, so good. So now let us talk of the drawbacks. What is the trouble of such linear regulators? And the trouble is the power dissipation. So the power dissipation by equation is P is V into I, where V is basically the difference in the voltage, the input voltage different divided minus by the output voltage multiplied by the current. So assuming this circuit works at say 1 ampere or is able to deliver an output of 1 ampere, the Vin is assuming to be 12 volts you're taking for example, and V out is 5 into 1 will actually make it somewhere near like 7 watts. Big deal. You might be assuming like 7 watts for a transistor to dissipate power is not a big thing to worry about. But no, it is a thing to worry about, and the reason is because of the junction temperature of the silicon. So if you see the data sheet of regulators, the thermal junction coefficient is somewhere around like 60 to 65 degrees Celsius per watt. So assuming we take 60 for now as a number, and dissipating 7 watts of power will actually cause around 420 degrees Celsius temperature at the regulator, and this is a trouble area. Though there are solutions in which heat sinks can dissipate a good amount of power out of these regulators, but usually it is not advisable to use such sort of regulators where the voltage drop is very high or the current requirement is of a larger number. So to summarize quickly on what we have discussed so far on linear regulators, there are like basically three types. One is a variable voltage regulator with this resistance R1 and R2, and these sort of regulators can take voltage input from say anything like say 5 volt to say 30 volts and can deliver an output of around like 2.5 volts to say whatever like 18 volts or so. This has a dropout voltage of 2.5 volts or above. That means the Vin actually needs to be more than 2.5 volts. So the Vin requires to be more than like 2.5 volts usually. Variable different transistors have different characteristics of such sort like 2.5, 1.5 or 1.8. But typically 2.5 is the number. Second category is the fixed voltage regulators. In this, it has no feedback loop, external feedback loop rather, and it gives a fixed output voltage of say 5 volts or like 9 volts and so on and so forth. Input voltage can be something like 12 volts, 15 volts, so on. The coupling capacitors in all of them, if you can see, they are like, so one coupling capacitor will be here also. These coupling capacitor actually suppresses or smoothens the ripples that happens on the input and the output of these regulators, which gives a much more smoother DC output. And third one is the LDO. So LDO, as we talked earlier, was capable of delivering with even like lower dropout. Input can be around like 1.5 volts. Output can be somewhere around like 1 volts at say 1 amperes, or even like 1.2 volts at 1 amperes. So this LDOs are capable of working at low voltage inputs as well, whereas here it has to be input voltage has to be more than 2.5 volts. Same the case in this where Vin has to be more than like 2.5 volts. The linear regulators come in this sort of a form factor transistor. I can try to show it close. So it has 3 pins. This is the connection for the heat sink. One is the input terminal, which is a V in, the other one is a V out, and this is the third terminal, which is either the ground. So I've taken a fixed regulator here. As we have seen, the linear regulators, everything is very nice, cheap, easy, but the trouble is power dissipation. So what is the solution? The solution is switching regulators. These dissipate less power even at huge drop across V in and V out for higher current values. But they're a little bit complex to design. Let us now discuss on switching regulators operation and functionality. Okay, so now let me try giving you some explanation of how switching regulators actually work. But before deep diving into switching regulators, let us try understanding a simple electrical circuit. Here we have a voltage source Vn and a switch and the load resistance RL. So once we close the switch, current flows through this loop, and when we open the switch, current stops. Assume that we have a Vin of around 12 volts. So switching this switch constantly at say 50% duty cycle on and off, the waveform will look something like this sort. If you closely look at this waveform, the average for a 50% duty cycle will be somewhere around like 6 volts. So this is the main fundamental theorem of switching regulator, that it switches the input voltage on and off at an extremely high speed to give an average voltage which is much less than the actual voltage, or rather Vin, the input voltage. The next thing that we do is to place one inductor coil here in series with the load resistance. So now what will happen is, when the switch closes, as the property of the inductor, it will oppose a current change. So as soon as switch is closes, immediate change of current will not appear across this or through this inductance. So assuming when the switch was open, the voltage down here was 0 volts, and same 0 volts appeared here at this terminal, and therefore no current was flowing through this loop. Now as soon as the switch closes, and since the inductor will oppose a current change, therefore this voltage will not instantaneously vary. So the current will start raising slowly, because eventually it has to rise. Power supply is alive, that's the reason. And then it saturates. And once it saturates, this guy behaves like a closed circuit, like a short circuit. And during this time, when the current was rising through this inductor, this charges the magnetic field through this coil. It saves as a current battery. And as soon as this switch opens up, this inductor acts as a current battery and drives this load, and the current will start slowly dropping out. So when the switch was open, there was no current. When the switch closes like this, the current slowly raises through this inductor, and the current passes through this load resistance. Once the saturation is reached somewhere at this point, this inductor will act as a short circuit, and once again, when this switch is opened, this inductor now will act as a current source. So it will feed the current through this resistance. Whereas the voltage, if you see that when the switch was closed, was like initially there was no voltage drop across the inductor. And if you see when the switch was closed, there was a sudden change in the voltage because the current cannot change. And then the voltage drop will slowly happen till the time the inductor is fully charged. So this is the voltage and this is the current I. Again, this whole phenomena is repeated when the switch is again closed. The current starts rising up in the next cycle, and then again discharges when the switch is closed, and this process continues. Whereas the voltage in the beginning, when the switch closes, will be looped high, but then in the next time when the switch opens, that time suppose a value V was present in this terminal point of the inductor, and current was flowing through, and since the switch again opened up during this duration and inductor opposes a current change, so this V will be present here and the inductor will act as a current battery. So there will be like a charge accumulation which will be happening here. A charge accumulation will be happening at this point, and since this is an open terminal, this guy will act as a current battery and try to drive current through this line. This charge accumulation at times might cause damage to this side of the electrical circuits, and therefore usually what is done is that we put one Schottky diode here which will drain out the negative charges just in case to avoid this damage of the components. So in the voltage curve, when the switch opens up, this time the voltage will be sharp negative and then again starts to come back to the 0 volts where it was earlier, and during this time this is a dissipation which has to happen through the Schottky diode. I mean these charges, the voltage charges. So now understand it in a simpler manner. The switch initially open, no current through RL. Switch closes, current slowly starts flowing through this inductor and then eventually through the load resistance. Switch opens, the inductor acts as a current source, continues to feed the same constant current, closes again, charges inductor, opens up again, feeds the resistance. This is how the current is maintained in a on-off manner through the load resistance. So we have taken care of the current overshoots by adding one inductor here, and now we'll take care of the voltage overshoots by adding one capacitor here. So this is what happens when the switch is closed. There is no voltage across this capacitor or the load resistance and no current is flowing through. As soon as the switch closes, two things will happen. Number one, the current will flow through the capacitance because the capacitance actually opposes a voltage change, and the current will also flow through the load resistance. During this time, the charges coming from the voltage source will start accumulating on the capacitor plates. So when the switch was in the closed condition, so this is the time suppose t, when switch was in the closed condition, the voltage across the capacitance was 0. Once the switch is opened up, the voltage slowly rises across the capacitance till it fully charges the capacitance, and then once the switch opens up, the charges flow from the capacitance through the load resistance and the charge across the capacitor diminishes. Again the switch is closed, again capacitor starts charging. Again the switch is open, the capacitor discharges through this resistance like this, and so on it continues. Whereas if you draw the current through this capacitance, as soon as the switch was closed, instantaneous current will flow through the capacitance and then it will decay out because the capacitance is actually charging, and every time the switch is closed, current will flow through the capacitance in a similar manner. So what we are trying to do with this is that by fast switching of this switch on and off, we are trying to smoothen out the output voltage appearing across this load resistance through this capacitance. So switch is open, capacitor charges and current flow through this load resistance. The switch is open, capacitor discharges and acts as a battery for the voltage and feeds the load resistance. So now let me try explaining you one more important building block component of the switching regulator. It is a comparator circuit. So this is the block diagram of a comparator. It has two inputs, one is inverting input, one is non-inverting input. Assuming that if you feed a constant sawtooth waveform or a triangular waveform to the non-inverting input, and we feed a DC voltage of say various different level to this inverting input. Let us see what actually happens. The property of this comparator is, if negative is more than positive, then output is negative to the maximum negative voltage available here. So assuming this is say 0 volts, so A if A is more than B, then output is 0. Whereas if A is less than B, means B dominates, the output is positive. Positive means the max level of the voltage at which the operator and the op amp is working. So here are the two inputs superimposed on each other, and let's see what actually happens. During this time, sawtooth value or the triangular wave value is less than the DC value, means negative value is higher than the positive value. So output is actually 0. During this time, when the triangular waveform is higher than the flat line here, or this value of the DC voltage, the positive value is high during this time. So therefore the output will be high. Again, during this time, the triangular waveform is lower than this input voltage, so output is again 0. So on. It moves. Something like this. Now what happens here at this point, when the input voltage drops, the amount of time the sawtooth input is higher than the other input, the DC voltage input, is for longer duration of time. Therefore, the plus output will be for longer duration of time compared to the previous ones. So here, if you see, we get an output which is in contrast with the input what we are feeding it at the A terminal or the inverting terminal. So on it moves. And here again, since this time is short, we get a very thin pulses. So what we achieve out of this is we have achieved a waveform with a varying duty cycle which is proportional to the input waveform. So input is at one level, say level 1, we get some value of duty cycle during this time. Say it's say 20%. The input is lower during this time 2, we get a different duty cycle during this time, which is say 60%. The input is much higher during this time 3, we get a different duty cycle of say 10%. So what we achieved here is that we are able to generate an output waveform which follows the input level of voltage, and this is known as a PWM output. PWM stands for pulse width modulation, means the width of these pulses are modulated or are varied in contrast to the input voltage. And this is a very important concept of switching regulators, because this pulse width modulation output actually triggers the switch that we talked a little bit, I talked earlier, to generate the output from the feedback which comes from the output at these terminals. I will try to explain you with the overall picture of the switching regulator. So now here is the complete circuit diagram of a switching regulator internals. The regulator inside generates few voltages like a 12 volt, 5 volt and 2.5 volt reference voltages. Since these voltages are basically reference voltages and does not draw any current, that's why these voltages do not vary and almost like a constant value. Now let me try mapping the components that we have been talking so far. This part of the circuit is a switch. So that mechanical switch is now what we replaced by a PMOS, an electrical switch. And the Schottky diode, the inductance, capacitance, and the load resistance. Whereas this is the comparator that we had been talking a while ago, with a sawtooth input of around like 150 kilohertz and an error amplifier, as you've seen in the earlier linear voltage regulator circuits. So let's see how this works. Assuming there is load resistance which is not varying and it has to generate some sort of a voltage output V out, the feedback taken from this voltage output is fed to the input of the error comparator or the error amplifier, which functions similar to that of a linear voltage regulator, as earlier we mentioned, with a constant Vref. So this output of this error amplifier will have some voltage, which when compared to the 150 kilohertz of triangular waveform will generate some sort of a duty cycle, a constant duty cycle rather, which will turn on and off this MOSFET so as to feed the current and generate this constant voltage and constant output. Constant voltage and constant current at the output, I'm sorry. Let's see how the regulation actually happens. Assuming the load resistance reduces, means it is hungry for more current. In that case, the current IL will actually increase. So once current IL increases, the V0 tends to drop. Once V0 tends to drop, the V0 is taken as a feedback loop here to this error amplifier, which will also drop. Once this terminal drops, in the process of maintaining the same voltage between these two junction points, the operational amplifier will try to increase the voltage here, because this guy will now dominate. Since this guy is dropping, this has to dominate. So this guy will increase. So once this voltage increases, comparison with the sawtooth waveform will have a duty cycle something like this. Because remember, as I said, like if voltage is high and sawtooth comparison will have less duration of time where this remains high, therefore it becomes a low duty cycle. And since it is an inverted MOSFET, a PMOS, the low duty cycle will allow the transistor to be on for longer duration of time, which is during this time. So when this output is off, the transistor is on. This makes the transistor on for longer duration of time and thereby feeding more current from the supply voltage, which now helps to bring back VO to a level of the regulated supply. On the contrary, when V out increases, the V feedback will also tend to increase, which in turn now will generate a lower voltage at the output of the amplifier. And since the voltage has lowered at the output of the amplifier, the comparator, if you see, the output, if it reduces, comparing the same sawtooth, will now generate a PWM of a wider duty cycle or a higher duty cycle. This will allow less time for the MOS to be on. This is the time when the switch is on. So when the MOS is on for less amount of time, it will draw less current from the main supply source and thereby reducing VO or the output voltage. Let me try to explain this again quickly to summarize everything. If load resistance reduces, it will be hungry for more power and thereby increasing the current requirement. Henceforth, V0 will reduce. Once V0 reduces, the feedback current here will also reduce, which in turn will increase the output of the error amplifier here, and thereby, once compared with the comparator, the duty cycle will reduce. And since the duty cycle feeds an inverted MOS, a zero value at the reduced cycle will make the MOS on, and therefore this MOSFET will be able to take more amount of current because it is now getting on for a longer duration of time to feed in more current and more power through this inductance and capacitance to this resistor RL, thereby bringing back VO to the same level where it was before. So I hope I'm able to explain you the functional operation of this switching regulators. This is how the switching regulator modules actually look like. So if you place it something like this, if you will notice it, this is the input capacitance which you have not drawn. This is to suppress the fluctuations of the input voltage supply here. This guy here is the inductance, which will be this one. The capacitance is this one. The variable resistance is here, which actually is a variable. If you vary this resistance, this output we can vary. And this is a Schottky diode, which will be somewhere here. And the IC comprises, or the integrated circuit comprises of the complete circuitry, which includes the 150 hertz generator, the reference voltages, internal regulators, the MOS, and so on and so forth. So I hope I'm able to explain you the concept of switching regulators to some extent, and I hope this lecture is helpful for you guys to understand. In case you have any further questions, you can drop me a message or else drop an email. We'll be happy to reply that. And one more thing, I will request, in case you guys want to hear something more from us on electrical circuits, please feel free to message us. And before closing, let me try to summarize what we have discussed so far. So, quick comparison between the linear regulators and switching regulators. The linear ones are these. They're cheap, they're simple, but they eat up a lot of power and they heat up a lot. So this is power hungry. These are switching regulators. They are of a little bit higher price than the linear regulators ones. Little bit more complex because it involves so much of circuitry. But the good thing is dissipates much less power. Hope I'm able to explain you the concepts. Thanks for watching this video. Bye bye.